Filters can be used to condition a signal and detectors to identify interesting activity. The Sense Filter Detect model captures the steps necessary to process a signal into an event. Sensing captures the physical signal. Filtering prepares the signal for detection. Detection identifies a set of features that correspond to something of interest. We can process our signals in several different ways. Analog circuits can process continuous signals. They can be very responsive and efficient, but also introduce noise and distortion. Digital circuits can perform certain functions at high speed and low power, but require significant design effort. Software can perform a wide range of functions, but at some penalty in speed relative to either digital logic or analog circuits. Many applications make use of all three of these methods. Signal processing bridges the analog and digital worlds. A signal represents the evolution of a physical quantity over time. We use the word signal for both continuous analog and discrete digital behavior. In the digital case, a time series is a sequence of sample values that represent the signal. This plot shows an analog signal captured on an oscilloscope. The x-axis represents time and the y-axis represents the signal value. This signal is continuous in time and can be measured at any point in time. The signal is also continuous in value and can take on any quantity within the physical limits of the phenomenon that produced it. Digital computers can't operate directly on analog signals. Instead, we use circuits to convert from analog to digital. An analog to digital converter, or ADC, turns the analog signal into digital form. The ADC samples the analog signal when it receives a command and returns a digital value at a given point in time. The result is one digital value per sample. Several different types of ADC architectures have been developed to provide different trade-offs between precision, sample rate, and cost. Generally speaking, ADCs that are both precise and fast will be expensive. Part of the design process is to choose the right ADC for the job. A digital analog converter, a DAC, or a DAC, allows us to transform a digital value into an analog signal. Here, a sequence of values represented are fed into the DAC. The typical DAC holds an output value until another sample is received for conversion. This gives a stair-step waveform. Increasing the sample rate improves the fidelity of the DAC waveform. This sine wave was generated using a digital analog converter fed by a table of output values. The waveform is generated as a sequence of steps. At each step, the DAC puts out a new value, then holds it. Sampling of signals produces a discrete time series, or simply time series. The time series is a set of sample values x sub I. How often do we need to sample? The Nyquist theorem provides an answer. A signal can be represented as a sum of sinusoidal components over a range of frequencies. If the highest frequency component has frequency f, we must sample at a rate of at least 2f to fully capture the signal. This is known as the Nyquist rate. Sampling above the Nyquist rate allows us to capture the sinusoid accurately. Sampling below the Nyquist rate will give us a distorted view of the signal because higher frequencies in the signal are aliased into lower frequencies. A filter can be used to condition a signal. A detector can be used to identify interesting activity in the signal. We can use a dot product to compute a finite impulse response, or FIR filter. An array X holds the sample values. The coefficients of the filter are held in B. The output of the filter at each time point is the sum of the pairwise products of the B's and the I's for the window of the filter. Here's the operation for an FIR filter of size 3. As the filter generates successive samples, the window moves to apply the coefficients to different parts of the signal. Signals must be sampled at regular intervals. Jitter in the sample rate, that is, variations in the sample rate, can result in distortion of the signal. Here's a computing platform for signal processing. A DSP is a digital signal processor, a CPU that has some specialized operations For example, the multiply-accumulate operation we just saw. Several types of operations on digital signals are very useful. Here is an average computed of 3 values in the original signal. Here's a difference between a sample and its previous value. This decimated signal has 1/4 the sample rate of the original. Each sample in the decimated signal is the average of 4 samples in the original signal. A detector performs a test on a value or a set of values. The simplest form of a detection is Boolean. Classification is simply several detections operate in parallel. Thanks for watching.